Yeah, hi and welcome back everyone to the supplementary coding along video series for the Build a Large Language Model from Scratch book. Here we are now going to talk about chapter 2, working with text data, which means essentially that we are going to prepare the data that we are going to use to train the LLM. Yeah, just to go to the chapter itself, chapter 2, you can see there are lots of sections. Starting at the top, the goal really here is to prepare the data set for the LLM. So there is actually a nice figure here that shows you this step in the grand scheme of the whole LLM building process. So here building an LLM means setting up the data set, coding the attention mechanism, coding the LLM architecture, and so forth. This is really the first stage of training the LLM, and then the pre-training comes in stage 2, and then later on in stage 3 we will be fine-tuning the LLM. But just to keep things focused, here we are going to talk about preparing the data set. And yeah, to give you another view here, essentially what we are going to do is we are going to take text and tokenize it and then convert these tokenized subparts of the text into token IDs, which we will be then encoding into vectors. I know this is maybe a bit fast here in this video. So I mentioned before, the videos are not as detailed as the book itself, and they're more focused as supplementary resource for the coding examples. But yeah, just to give you the big picture here. So the goal is really to prepare raw text data so that the LLM can then process it. It's really that the LLM works with text, but we have to first convert it into a format that it can be that can be read, let's say, in a form that the LLM understands, which in that sense here is actually vectors, like mathematical vectors. And if I scroll up a bit, it's really like the idea also that vectors are numeric representations here of this text. So that is our goal, going from letters and words into a more numeric representation, which can then be used later on during the pre-training to optimize the weight parameters of that LLM. But yeah, I don't want to go too far ahead and talk about pre-training. The focus here really is on preparing here the input data for the LLM. And specifically in section 2, tokenizing text, the focus is really also only on this sub part here at the bottom, where we take some input text and we break it down into individual smaller chunks. And and this is a process known as tokenization. Just to show you an example, so we will be using a library called TickToken later. And there is, I think, a nice virtual visualization, tick tokenizer, when we go here. And they do have different LLMs. For example, there is this GPT-2 LLM. If we type some text, let's say hello world, something like this, this is a test. So here you can really see how it's broken down into individual tokens. So you can see hello is a token, the comma is a token, world is a token, dot is a token, and these are the token IDs. We will get to the token IDs later on, how they are created. For now, the focus is really like to just break it down into individual parts. And we are not going to implement actually the exact same algorithm that is used here. I do have some bonus material on doing that we'll share later. Here, first, we want to do the big picture level of how we can actually break down text into individual chunks. So one way would be essentially to use just regular expressions. But starting sequentially, like how I did in the book, let's actually download the data set first, and we will be using the data set later in this chapter to actually implement the data loaders in PyTorch. So let's start with a data set here before I go too much ahead and talk about all the other things. So we're going to use a library OS, which is just a standard Python library, and URL lib request, which is also a standard Python library. This is usually for working with files, and this is for downloading things from the internet. So the data set we are going to work with here, it's called the verdict. So let me just go here and maybe a new tab. And the verdict is a short story by Edith Wharton. So it's available as public domain data. I think there's a Wikipedia version that is actually quite nice here. So this is a very short story here, and I picked this one as the data set because we want to keep things simple, that it doesn't take too long when we are actually pre-training the LLM, because it's more for educational purposes. And it's also, pretty simple, readable, and most importantly, it's a public domain data set or book. So that means we can use it without having to worry about copyright restrictions, for example, in the United States at least. So in that case, this is an open public domain data set. There is no concern using this, for example, for LLM training. Okay, so we would download this data set. So we could, what we could do is we could go here, just copy and paste this, and create a new file, a text file, insert this and save it and so forth. I have a little bit of a quicker way here. So let me just copy and paste this. I have it also in the GitHub repository for the book. And so this link is a URL link to the place on GitHub where I provided this data set, just in case, in the future, the data set might become unavailable from Wikipedia or something. Here you can find a version in the book's GitHub repository, RASBT LLMs from scratch. And in chapter 2, in the first folder, main chapter code, I included the verdict here. And if you want to copy something from GitHub as raw text, you have to click on this raw here, and then you get the raw text, which in this case, as you can see, is similar to what you can see on this page. So if I copy this URL now, insert it here, it's really the same URL that you have seen earlier without all the line breaks. When I execute this code, it will download this data set and save it to a file, the-verdict.txt. Let me do that. And then maybe refresh here. And you can see it's now in this folder. So it's locally now on our computer. The next step would be opening this file in Python. So right now it's just sitting in our computer. And the next step would be opening this. So let me just copy this. And we are just reading it, so the R here. And then on Windows, it's, I think, required to specifically say which encoding we're using. So UTF-8, the standard encoding. And then we can just read the raw text here. And then let's double check. So we can double check that the text looks okay. So we can see, the Python interpreter has successfully loaded the text here. And we can also just double check, how long it is. So I maybe recommend running this if you're running the code to check that you get approximately the same number here, which means you're not missing any characters. So it should be about 20,479 characters if you loaded the dataset correctly. So let's now briefly introduce the concept of tokenization with regular expressions, which is just like a warm-up before we use the real, let's say, tick token library for tokenization. So we are going to use a Python regular expression, and let's actually use some simpler text. For the warm-up here, let's use the text I just typed in here and provide it here. Then we can type result and then the regular expression. And I must say that regular expressions are my weak spot, so I'm really not that good at them. But honestly, nowadays with LLMs like ChatGPT, it's actually pretty easy to figure it out. So this is essentially just a regular expression that splits on white space characters. And by the way, you don't have to really know what regular expressions are for the bigger context of training LLMs, because we are later using a tokenizer based on byte pair encoding. And I also have a from scratch implementation. It's not in the book, but it's in the supplementary materials that I can also maybe show you later. But yeah, for simplicity, our goal here, if you remember what I mentioned earlier, our goal here is first to split up this text into individual tokens. So let's do that with this regular expression and then maybe print the result and see how it looks like. And so yeah, we can see we have now the individual words and we have white space characters and so forth. One thing we might want to do is also to have the punctuation as separate characters. So for that, we would have to make a little bit of a more sophisticated regular expression. And like I told you, I'm not very good at regular expressions. So let me just copy and paste it here. So this is now a regular expression that is slightly more sophisticated. So this one will also include the punctuation as separate tokens, where before they were part of the word itself. Okay, so this is our simplest way of tokenizing. Now, as you have seen here, if I go here, there are actually no white space characters in the output here. So one thing to mimic this could be, for example, that we are also going to strip the white space characters. This is just like an optional thing we could do. We can just get rid of the white space characters. So here I just have a simple list comprehension that will strip out, the white space characters. So you can see now that is the result, without white space characters. It's a bit different from what you see here, because this is a sophisticated byte pair encoding algorithm, and I will talk more about this later. I will share some, we have a dedicated section on this actually. But so here, for now, we're just building a very simple version of that to understand roughly, what we are doing here, like how we are tokenizing text. Doing it a bit more advanced now, I mean, this is a nice way to handle simple cases, but now imagine we have a more complicated case like that. So this will actually fail really. That doesn't really take care of special characters like, the double dash and everything. So we can actually make it more sophisticated. So I have now like more sophisticated regular expression, and also again the white space stripping, and that does a good job of separating words and special tokens. So we did a lot of work here now to prepare our text by splitting it into individual tokens and punctuation characters. So we tested it on this simple example, but let's actually use this on our real text. So for that, what we have to do now is we have to actually use our raw text. Well, raw text is what we have here at the top. So that's our raw text. Let's actually see what happens when we do that. So we tokenized our raw text, and now let's see how many tokens we have. So we have length of, let me actually save this as a variable, because this is a lot of code. Let's just call it preprocessed. And then, so we have here 4,690 tokens. So what we have done so far in section 2.2 is we took raw text and we tokenized it. And now in the next section, we will be talking about converting this raw text into these so-called token IDs. Let's now talk about converting the tokens into token IDs. So previously we talked about breaking down the text into individual tokens here. And now in this video, we are going to talk about converting the tokens here into token IDs, which are so-called token IDs, and they are essentially unique integers. So how do we do that? The first step, let's maybe go to section 2.3 here. The first step would be building a so-called vocabulary. So the vocabulary is the unique mapping between each word that can occur and a unique integer. So for example, for simplicity, if we have a very small data set here, the quick brown fox jumps over the lazy dog. The first step would be breaking down the text into tokens, which we have done before. And now we are going to sort them alphabetically, making sure we don't have duplicates in there. And then we are going to assign a unique mapping here to integers. So how do we do that in Python? So we already have the preprocessed from the previous section. So preprocessed is all the unique tokens in the data set. And so what we can do now is we can get rid of the duplicates first. So we can do set preprocessed, which will get rid of the duplicates. And then let's also sort them with a sorted function in Python. And we can assign all words a variable to hold them. So let's just make sure it worked. So we can see these are all the unique words. It's a lot of words. We can actually also look at how many we have, how long this list is. So that's about 1,130 words. So it's 4 times smaller than preprocessed. So we had a bunch of duplicates in there. Let's actually save that for later. We call that the vocabulary size. So how many unique words we have. And so the vocabulary size is shown below 1,130. So next, let's actually build the vocabulary. This is actually quite simple in this illustration for educational purposes. What we can do is we can, for each token, assign an integer, a unique integer. For each integer token, enumerate all words. So what it will do is it will iterate over all the unique words and then assign in ascending order these integer labels. So we can actually take a look at this. So you can see it's essentially mapping each word to an integer here. And this is essentially what we are doing here. So now we have the vocabulary. So maybe going to the next figure. So the next step would be, now that we have this vocabulary, we use this vocabulary to actually tokenize training data into token IDs. You can see the vocabulary is in a sorted order, so we have them alphabetically sorted with this mapping. And now for any new text, for example, the training text, but also later on when we want to use the LLM, we are going to use this vocabulary to convert any text into token IDs here. So basically using the vocabulary mapping, if we have the word the, we would find the word the in the vocabulary and find the corresponding integer, for example. So the here, it's not shown because it's too long, would correspond to integer 7. And then the second word, brown, would correspond to integer 0. And then dog would correspond to integer 1 and so forth. And so this way, we are going to encode the given text into these token IDs. So let's do this in Python. So I will actually copy and paste here, because otherwise it will take too long if I just type it, and I will make errors, because typing in front of a camera is quite different than coding in silence. But so here what I'm going to show you is a simple tokenizer class, and that's a Python class. And that does the following things. So init is usually executed when you are instantiating a new object, which we will be doing later. Let me just maybe first explain, and then we will create a new object here. But so init is the constructor. It takes a vocabulary and it defines, or it will just save the vocabulary as the string to integer mapping. So string to integer means that we are mapping from strings to integer representations. And then we also have the same thing inverted. So we are here, instead of having is, we have si, which inverts string and integer. So what it will do is it will create this mapping from integer to string now. So we have integer and string, inverting this essentially. So here we have now two vocabularies, the regular vocabulary and the inverted vocabulary. And then we have an encode method that takes any text and uses the regular expression from section 2.2, and breaks down the text into tokens. So this is what we have seen earlier. This is quite a long vocabulary if I scroll up. So let me actually maybe comment this out. So earlier in the previous video, we have broken down text into tokens. So we used this regular expression. So here we are just going to reuse that regular expression from earlier and then strip out the white spaces. And then here, this is the interesting part. This is where we are creating the token IDs. So we are going to use the vocabulary from here. And for each token or string in preprocessed, we are going to convert it. So just to show you what that means. So if I just take, let's say, Jack here, and I pass it to my vocab. So if I have something like this, so this should give me an ID, right? So this is essentially, the token ID. And I can also maybe just show you to create a reverse mapping here. So if we want to go back to string and type 57, this should give us the original word back. So this is basically what's happening here. We have a vocabulary, inverse vocabulary. Here we are just going from string to integer. So string to integer means this one here. We are going from a string to this token ID. And we do that for each token ID in the data set here. And the data set is the tokenized version of the text. And this is really it. And then we have a decode method, and the decode method goes backwards. So here we are going to recreate the text by mapping back from integers to string, which is what I've just shown you. So integers to string means that we go here from the integer back to the string. And I think, this might be relatively, complicated, maybe not, but it's a lot of information. So in this case, let's actually use it, and I think it becomes more clear when we actually use it. So let's do simple. Unfortunately, I don't have autocomplete here, so let me just copy it from here. Let's actually just instantiate a new object using the vocabulary. Like this. Oops, not defined. I need to execute this cell first. This always happens when I talk and code at the same time. I forget things. Then let's just use some text here. Instead of me typing it, I'm just copy and pasting it. And so the first step is converting text into these IDs. So let's do tokenizer.encode and then text. So this is essentially calling this encode method. And then we will hopefully see that those are converted into token IDs. So we can see now this would be the token ID representation for this particular text. And we could also go backwards. So if we have these token IDs, we can do tokenizer.decode and IDs, and this would correspond to this code. This will be converting this back into text essentially. And what's nice is you can do also the round trip, which means what we can do is, let's do it like this, decode and then put this encoding inside here. And this should give us the original text or something that is close to the original text. You can see there are a few slight differences. For example, here we have this additional white space, for example. But overall, this works quite well. We have a way of converting text back into from token IDs back into text. So this would be a very simple tokenizer. That's not the real tokenizer that is used by GPT models. That's why I'm calling it simple tokenizer. But I think this illustrates the concept of tokenization quite nicely, how we go from text into integer presentations. And now in the next video, we will talk a bit about special coding, special tokens, and how we handle those. All right, let's now talk about adding special context tokens. So previously we talked about creating the so-called vocabulary from all the different tokens in the training set. And then we use that vocabulary to create the token IDs. Now we are going to talk about extending this vocabulary with special tokens. So for example, we might want to add, depending on the tokenizer, a token for unknown words that are not in the training set. Or for example, we could indicate when the there's an end of the text by using a so-called end of text token. And we will talk more about this end of text token later on when we are actually pre-training and fine-tuning the LLM. So here, though, the goal is essentially to extend our simple tokenizer a little bit to handle these special tokens. And I also wanted to just show you one shortcoming of our tokenizer. So if I go up here, we defined our simple tokenizer here. Based on the vocabulary. If I have some text now that is slightly more, I would say, sophisticated. So before we used this text here. If I have text, let's say, let's do something not super sophisticated, but something different, like hello, maybe do you like tea? Is, I don't know, this a test, for example. And let's try to see what our tokenizer does when we actually try to encode this. So as you can see, there is an error now. It says key error hello. And hello is a very normal word, so why would there be an error? And the reason is because the text that we processed apparently, so the verdict here, apparently it does not contain the word hello. Now, if you are creating an LLM and train it on trillions of tokens, the chances are that this word would be in the training set. For example, here we have only this very small data set. It might not even contain simple words as hello, for example. And by the way, later on, I will also tell you more about an algorithm that can naturally handle unknown words. So for example, if the word is unknown, it will just break it down into individual characters. So maybe to show you what I mean. So if I type just something like this, you can see if it doesn't know the word, it will break it down into individual characters. But this is a more advanced algorithm. For now, how can we actually make our simple tokenizer slightly more sophisticated by handling unknown words? So what we could do is we can extend our tokens. So if we have all tokens, which were the list of the preprocessed text tokens or words. So this would essentially recreate our unique tokens from the data set. And now what we could do is we could actually extend it. So if we use the extend method on Python lists, we can actually add additional tokens. For example, we could add this end of text token that I mentioned earlier. Or we could also add a token for unknown words. So we can really add anything we like here. So just extending it. And so the difference is to what we did before is we are creating it similar to before, but now we are adding tokens that are not already in the data set. And then we would generate the vocabulary similar to before. So this is the same that we used before, like this token to integer mapping for the vocabulary. And then, let's actually take a look at the length of the vocabulary. I think before we had, let me scroll up a bit, 1,130. Now we should have 1,132 tokens. Let's double check. Yep, so we have these 2 new tokens added. And let's actually print the first or the last, in this case, the last 5 entries. We can do the first 5. They should look similar to what we've seen before. So just the special characters, but more interestingly, let's actually print the last 5 tokens in the vocabulary, and we can see we now have these 2 new special tokens in the vocabulary. In a similar way, we can now modify our simple tokenizer to actually use these special tokens. So what we have to do now is we have to essentially add a special rule to process those. So I will just copy and paste it here. So we return the string if the string is not empty and if it's in this vocabulary. And otherwise, if it's not in the vocabulary, so else, we will return unknown for this unknown token. And this way we will prevent that this modified version of our simple tokenizer crashes on words such as hello here, for example. And this is all we do. Essentially, it's a simple modification, and this should actually help us to run our simple text example. Let's just copy this one for simplicity. So we are reinitializing the tokenizer. Now we have tokenizer version 2, and I will make a new code cell and then tokenizer encode text, and this hopefully works now. And yeah, you can see we now have this unknown token. So actually when we go back, let's see what happens. So tokenizer decode. Yeah, you can see now it handled the unknown tokens. This is of course not desirable if we want to regenerate the original text. And later, actually in the next sections, I will talk also about an algorithm that will make this a bit more sophisticated. It's called byte pair encoding, and I will explain how byte pair encoding handles unknown tokens. Let's now talk about byte pair encoding, which is an algorithm that will help us to take our tokenizer to the next level. So byte pair encoding is an algorithm that has been around for about 30 years or so, but it's really popular for implementing tokenizers these days. And for example, GPT-1, GPT-2, 3, and 4, they are all using this byte pair encoding algorithm for their tokenizer. And even other companies, for example, Meta AI for their recent Llama 3 models, they're using byte pair encoding. And so byte pair encoding really helps us addressing one major shortcoming of our tokenizer. So if I go up again a few cells here, one of the shortcomings of our simple tokenizer was that it wasn't able to handle unknown words. So for example, in this case, we had this word hello, and since hello was not represented in the training data, it would raise a key error. And so the way we handled that was that we replaced unknown tokens by the unknown placeholder token here. So we had this special rule here to replace anything that is not contained in the vocabulary, so anything that it hasn't seen during the training, by these so-called unknown special tokens. So what happens is, for example, if we have some text like this here, so these unknown words get replaced by UNK placeholder tokens, and this one as well. But the main shortcoming of this is now to the LLM, this all looks the same. So the LLM doesn't really know what's here and what's here because it receives the same token ID for both of these cases. And in many real world tasks where you have specific names or anything that were not included in the training data, the LLM wouldn't have any idea what you are talking about or what you're referring to if you have multiple of these unknown tokens in your text and so forth. And yeah, this is not ideal. So the byte pair encoding algorithm is a way that it can always break down any type of word into subtokens. So to show you an example, let's go briefly to this tick tokenizer app again, and we will be in this video also using the tick token app, or sorry, Python library in a few moments. But if I type some, let's say some unknown word and then something like this here, you can see it's actually breaking it down into sub words. So what happens here, maybe let's fix this, it's even nicer. So what happens here is that I bet you that this is something that was not contained in the training data for GPT-2, but nonetheless, it's able to break it down into individual tokens without failing. So without raising an error or without inserting a placeholder token or anything like that. So what happens is it's breaking down longer unknown words into known subwords. So it has, for example, seen something like some in its training set or unknown. So these are unknown words. So you can see here, it's breaking them down successfully into individual subtokens. And then if we have a string like this, this is something that doesn't really correspond to anything in the training data. It would then always fall back to individual characters. So in this case, it will just use a single character as a token. So in this way, it will never fail because it will always fall back to these individual characters if there's an unknown word. Now, this is maybe a bit inefficient because now one word becomes a lot of tokens. So it's not the most efficient way to encode input text if you have a lot of unknown words. However, it will never fail in this case. So this is one improvement over our previous method, which would just replace unknown tokens with this UNK placeholder token. So if you're interested in the byte pair encoding algorithm, how it works, so OpenAI, they actually open sourced the inference method for this byte pair encoding algorithm. So they have this GPT-2 GitHub repository. So it should be just OpenAI GPT-2. And then in this folder, SRC and then encoder, they have the byte pair encoding implemented here to break down words or input text into these subtokens. Now, they don't share the training method for this. So they only share the code that you use when you have already trained this tokenizer. However, if you're curious, I implemented this from scratch. So if you scroll down here in the bonus material of the book, so this is my repository RSBT LLMs from scratch. And then you go to this byte pair encoding tokenizer from scratch link. This will bring you to a notebook, a Jupyter notebook, where this implements the byte pair encoding step by step from scratch, including training. And then also at the end, I have a method for loading the OpenAI weights into this. So this should work similarly to what OpenAI used for the GPT-2 model. So if you are interested in more details, I recommend checking this out. But know that this is only optional. This is pretty advanced, and this is also a very long notebook, which is why I didn't include it in the book itself. Because in practice, the book is about LLMs, and this is a whole different topic. This could be actually the topic of a whole other book because it's actually quite complex. So the main message here really is that we are going to take text, unknown tokens and everything, and we have now a way to break it down into individual subtokens with this BPE method. And in practice, we are going to use the library called TickToken, which is an open source library from OpenAI. So the book, the later chapters, will implement everything from scratch because that's the title of the book, Build a Large Language Model from Scratch. But I would consider the tokenizer not really part of the LLM itself. So in this case, the tokenizer here, we are going to use this library from TickToken because it's actually also very nice and efficient, and it's what most people use in practice. So the reason why it's efficient, for example, more efficient than this implementation here, this other implementation here from OpenAI, is that the most expensive function calls or code is implemented in Rust, where Rust is a different programming language that is often used to implement high performance code. And then to make it easy to use, people usually add a Python API around this. So we're going to use this library in Python, but most of the core parts are implemented in Rust to make it really fast in inference. So what we're going to do is we're going to import the TickToken library. Here we go. So the TickToken library is helping us then to use this GPT-2 tokenizer. And by the way, why GPT-2 and not GPT-3 or 4? That's because later in chapter 5, we will be training a small GPT-2 style model. And then we will also later see how we can load the pre-trained weights from OpenAI, who shared the GPT-2 model weights. Unfortunately, they didn't share the GPT-3 or GPT-4 model weights yet. But the architecture of GPT-3 is the same as 2 and so forth. In any case, so we are going to use the GPT-2 tokenizer to make it compatible to the model we are going to implement later in chapter 5. And we can import the TickToken library like this. If you have set up your Python environment as described in the first video with this requirements.txt file, this should automatically work. If you get an import error, that means you probably haven't installed the TickToken Python library, so you could either use uv pip install or just pip install TickToken to install this library. So if you would execute this code cell here, this would install the TickToken library. So, but I'm commenting it out because I have it already installed. And so next, let me also just briefly double check which version I'm using. So it's always a habit of mine to double check because you never know if you run the notebook in a few years in the future. Maybe if you get a different result, it could be due to a different version of the library. So I'm using 0.9, but it should also be fine if you have an older version like 0.7 or 6 or something like that. But if you get some weird results that don't really match what you expect, making sure you have the correct version is never a bad idea. So you could then also fix this version number like this, for example. Okay, so how are we going to use the tick tokenizer now? So we are going to instantiate a new tokenizer object, and we are going to use the GPT-2 tokenizer, like I mentioned before. So we do get encoding and then GPT-2 like this. And this would instantiate the GPT-2 tokenizer with the full vocabulary, the way it was trained and everything. So this is already ready to use. We don't have to train anything. And then the usage is exactly the same as our own simple tokenizer. This is why we went through all the work here implementing this, because it helps, I think, illustrate how encode and decode work, like these methods. And this, yeah, tick tokenizer is using exactly the same, the same API. So you can see we are encoding this now, and then there is also tokenizer decode like this, and this gives us back the original text, which is exactly what we had before. Now, let me actually show you a more advanced case where I have some copy-pasted some text here, and let's actually try to encode this text. So before I mentioned to you that it can handle arbitrary words. So it is actually able to, break down any words into subtokens. So let's see actually what happens. So you may notice now that actually it raises an error. And why is that? So there is one interesting thing about the GPT tokenizer. And so one is that they use the so-called special end of text token. And I think I glanced over this in the previous videos, but the end of text token is usually used, if I can find the figure here, it is usually used to concatenate texts. Let me double check. Yeah, here. So when you are preparing the data set for training an LLM, you usually have multiple documents. And to signal to the LLM where one document ends and where the next document starts, you usually add this end of text token. You can either add it at the beginning of the next document or at the end of the previous document. That doesn't matter. But you usually have this end of text delimiter to show where a new document starts, so that the LLM knows, okay, this is a new document now, it's not part of the previous document. And this is also used in GPT-2, for example. And it's a special token that they used, but it's not by default enabled in this tokenizer, which is why it's complaining. So what you have to do is you have to, unfortunately, add this as a special token. So you have to be very explicit here and then add this special token like this. And yeah, you can see this one works now. And so this end of text corresponds to 50,256, which is essentially the vocabulary size of this tokenizer. So the vocabulary has 50,256 entries in this case. And so one more thing I wanted to mention is it might look like it's not working well with things that is not denoted as allowed special, but it would work with any other token. So I can just, add arbitrary text here and it would work like this. So like we said before, it can break down arbitrary text. It was just an exception with this end of text token. And so this is in a nutshell how the byte pair encoding algorithm works. So it's essentially a method for breaking down arbitrary text into subword tokens. And if you are curious about more details, how it's implemented, I highly recommend or not highly, but I suggest checking out this source code. I would say I would not highly recommend it at this point because it's pretty advanced and it can be a bit confusing. And yeah, if you like, you can also check out my implementation here where I added a few more comments and hopefully making this a bit more readable. But yeah, again, this is advanced material. I would say this would be almost topic for another book. It's not really anything you have to necessarily understand for implementing an LLM. The core message is we have now an algorithm that breaks down text into tokens. And in the next video, we will talk about implementing the data sampling. Let's now talk about data sampling with a sliding window. So what that means is previously we talked about creating these subword tokens from a given text, and then we converted the subtext tokens into token IDs. And later we will learn how to convert them into vectors, embedding vectors, and then pass them to the LLM. But for now, the focus is really still on this part here. How can we do this efficiently? For instance, the LLM, it can't receive all the tokens all at once as input. So the topic of this section is how do we provide smaller chunks of these token IDs to the LLM efficiently so that we can later train the LLM efficiently. So let's go to section 2.6 here. There's one more thing I wanted to mention before we go to the code examples. LLMs, essentially one of the hallmarks of LLMs is that they are predicting one token at a time. So if we have an input text, for example, LLMs learn to predict one word at a time. If that is our input text, let's consider the first token. If we pass only this token, ideally the LLM should predict the next token. And here in the next row, LLMs learn the next token is 2 and so forth. So the goal is to teach the LLM to predict one word at a time. And this is one of the interesting things about LLMs. This makes them so efficient at scale in terms of being able to train them on very large data sets. In traditional machine learning, we usually as humans had to find ways to create labeled data. So here it's actually very easy because we can use raw text and the label creates itself by just being the next token. So we are just taking text, we hide part of the text. For example, here we hide this text, we provide one token as input, and then the next token is the target label that the LLM learns to predict. We will learn more about how this works, for example, optimizing a loss function, predicting next tokens, and so forth in later chapters. Here, the goal is to just prepare the data in a similar format so that when we pass an input to the LLM has then the next target that it can predict. So if I go to my code here, so what we are going to do is we are going to do this efficiently for the verdict data set. So just to provide it here again, the verdict was the short story by Edith Wharton that we downloaded earlier. And what we're going to do now is we're going to use the tick token tokenizer to encode this into token IDs. And if we do that, we can see we have 5,145 token IDs. So just maybe to visualize them, can see them. So these are all the token IDs in our text. And now the goal is how can we provide them efficiently to the LLM in the form of sub chunks. So you can see it's a lot of tokens and the LLM wouldn't be able to pass them all. So we want to, for example, provide chunks of 4. 4 because it's nice and small and fits into this Jupyter lab when we visualize it and I can make nice figures. But in practice, the chunks are usually much larger. They're usually 1,000, 4,000, 8,000 tokens at a time, depending on the LLM. Here, in the case of GPT-2, I think it was 1,024 tokens that were used at a time during pre-training. We are, in this particular notebook, only using 4 for visualization purposes, just so that I can show you some things more efficiently in a figure. So that is what I wanted to say here. And we are also going to use a particular subset. We are truncating the first 50 tokens just to have some nicer examples and some nicer text. But this is just like an implementation detail to make this visually a bit nicer. Now, what I wanted to show you now is the way we prepare the X, the inputs, and the Y, the targets. I kind of showed it to you here already that we are concerned always with the next target token here. So we are creating a data set here where the targets are the inputs shifted by one position, which then helps us to have the targets as the next token to the LLM. So for instance here, what I'm doing is I have this sample text. So the sample text is, it should be about 5,000 something. Oops. Tokens. So 5,095 tokens because I just truncated some tokens. So we have 5,095 tokens. And we have a context size of 4. So we are only considering 4 tokens. So here we are going to take the first 4 tokens and then we shifted by one position so that the targets are shifted by one position. So you can see it here in the output. We have the inputs and then the targets are shifted by one position. So if I show it like this is how it would look like, but it's a bit hard to read. So I inserted this white space so you can see where the overlaps are here. So you can see those 3 tokens overlap, and this would be the next token, and this would be the previous token that is not presented in the targets. So if the LLM receives this token, it's supposed to predict this token. If the LLM receives those tokens, it's supposed to predict this token. If the LLM receives those tokens, it should predict this one. And if it receives those, it should predict this one, and so forth. So that's the whole idea here. And maybe to make this a bit more clear, what I've just shown you visually. So here's some other code example, which is exactly doing what I just showed you, where it's showing the next token. And since this might be a bit abstract with these numbers, we could also just use our tokenizer. For example, let me copy this so it's easier than just retyping it. So we can use our tokenizer to decode the token IDs back into text, and do this for both the targets and the input context. And so this is the same. Oops, made a mistake. I probably forgot to close parentheses. So you can see what it would look like. So we are always predicting the next word in the sentence. And so to make this really efficient, we are going to use PyTorch, where PyTorch is a very popular deep learning framework. It's probably the most widely used deep learning framework today. And so we're going to import this and use the data loader and data set classes from there, because they implemented this very efficiently, and we're going to reuse these parts because they're not really part of the LLM. We are still talking about setting up the data set, and it would be a bit, tedious to reinvent the wheel and write our own data loaders and so forth. And so for that, we're going to use PyTorch. And so PyTorch is imported as torch, even though the library is called PyTorch. It's just a convention we have to remember. And if you followed the video in the first chapter, I showed you some setup tutorial. If you follow this and install the requirements.txt, this should already work. In case it doesn't work, it means you don't have PyTorch installed. And so one way to install it would be uv pip install or pip install, depending on how your system is set up, and just typing this command, and it should automatically get a good version for your computer. However, if you want to be more specific, for example, you can go to pytorch.org, and on this website, they have like this installer menu that has different commands for different computers. So for example, I'm running this on a Mac with pip, and then it would give me that this command. If you are on Linux by default, here this would be the CPU code. It would be a bit different. If you have a GPU, by default, if you type pip install torch, it would come with CUDA 12.4 libraries. So it would support the GPU with CUDA 12.4. But if you want a specific version, you can also change it, and there are different URLs. And by the time you are watching it, there might be a whole new set of CUDA versions. So this is really specific in terms of what GPU drivers you support. But by default, you can also just do pip install torch, and it should technically work. Now, back to this one here, I'm also just double checking which version I'm using here. So here I'm using version 2.6. And I should say when I started writing this book, it was 2.0, because that was the most recent version 2 years ago when I started writing the book. But I tested the book on all subsequent versions of PyTorch, and I couldn't see any difference in any of the code. On the GitHub repository, I also have automated tests. So each time a new PyTorch version comes out, I'm just double checking it still works. And so far, I haven't seen any difference in PyTorch that would make any of the code different. So in this case, you can feel free to also use older versions of PyTorch, for example, 2.0, 2.1, 2.2, 3, 4, and 5. They should work equally fine. However, if you notice anything that doesn't work, for example, the results look different, you could just try also to install this specific version of PyTorch by doing pip install PyTorch and then 2.6.0. And so this would then install this specific version of PyTorch I'm using right now at the moment. Okay, so this was a little detour. Maybe one more thing I wanted to mention is if you're new to PyTorch, it's essentially a deep learning framework. It's very relatively comprehensive. It has a lot of things, but we are only going to use a subset here in this book. It's essentially more of a linear algebra library with a few deep learning convenience functions. There are whole courses and books about PyTorch if you want to learn about it. But if you want to learn about it efficiently, I also have Appendix A here. So I've been using PyTorch, I would say, since 2018 for 7 years now, and I've taught many PyTorch workshops, and I wrote another book about PyTorch and so forth. So what I want to say here is, over the years, I used PyTorch quite a lot, and I was thinking really hard, what are actually the parts you need to know for this book? So, and based on that, I compiled this Appendix A, which is essentially a book chapter of 40 pages approximately that just go over the essentials that you need for basic LLM training and development, where this should get you up to speed relatively quickly. Of course, if you're curious, I recommend considering a whole course or a book on PyTorch at some point. But if you just want to get up to speed with PyTorch for this particular book, try to read Appendix A, and maybe it's already sufficient. It might be a steeper learning curve because I'm trying to keep things efficient and compact, but maybe this is all you need at that time to really get up to speed, so you don't, let's say, go on a detour for a few months to try to learn PyTorch, and then, then you get maybe frustrated or get bored. So I would suggest maybe trying Appendix A, and maybe it's already sufficient to get you up to speed here. Now, back to the data loading. So we talked about PyTorch and importing PyTorch. Let's actually go back to section 2.6, data sampling with a sliding window. So we talked about the target word, predicting the next word. And so now we are going to prepare the data set accordingly. So we are going to take the input data and we are creating these chunks. And I mentioned before, we're using a chunk size of 4 or context size of 4 for visualization purposes, so it nicely fits into this figure and so forth. But in reality, these are usually larger, like 1024 in the case of the GPT-2 model. Or newer models use 8,000, 16,000 tokens in each row, but it would be hard, of course, to visualize here. And so, as you can see, the one box here, the left box, that's the input X that we are creating. And then the targets are shifted by one position, as you can see here. It's the same idea what I showed you earlier. We are creating inputs and targets simultaneously from this text so that we can feed both to the LLM later when we are training the LLM. So let me actually do this in code. And for this, we are going to use a PyTorch dataset class. And so the reason why we're using a PyTorch dataset class is it will allow us to use the PyTorch data loaders later. And they are essentially a very nice and efficient way to create batches and to shuffle the data and to use multiple background processes to process the data faster. It has a lot of convenience added to it. So how a dataset looks like is we have a constructor here. We are setting them to empty lists. Then we are going to tokenize the text. So text is the input text we're going to pass. And so we get the token IDs. And here, this is the part where we are creating these so-called chunks. So these chunks are these two chunks, basically. And instead of, I should go back maybe one more time, instead of just creating one chunk for the inputs and targets, we're doing this for the whole data set. So we are storing these chunks here. We're adding them here for the inputs and for the targets. So we are appending them to these lists we created earlier. And it's the same concept as before. We are sliding over the input data set, and then the targets are shifted here by one position. So what we are going to do is we are taking this left box and we are going to slide it over the input. So you can see the first row is in the heart of, and then when we slide it over, the next one is the city stood the, and then old library and so forth. So it's sliding it over by one position. And it's If you have a very large data set, it's maybe not the way to do it because you can't store 15 trillion tokens in memory. So this would run out of memory. But if you have just a few books, a few gigabytes or megabytes of data, I mean, if you have, I don't know, 1,000 books or something like this would conveniently fit. So you don't have to worry about it and over optimize at this point. There are a few more advanced ways and tools if you are really training LLMs on trillions of tokens, but for here educational purposes we are keeping things relatively simple and readable because this is the basic approach, and yeah, so to understand also how things work under the hood. Now we have this data set now, and I mentioned the data loader that we want to use. So let me, instead of typing all the code, just insert it below. So the data loader is created here, and I have a function I'm defining that returns this data loader. And so here we are defining the text. We can set a batch size, a max length of each context length. So before we set 4 is our length here. We can also, this is just a default parameter, we can override it later. We set the stride, it's by how many positions we are moving the box. We'll get back to that in a few moments. Whether we want to shuffle the data set, whether we want to drop the last batch or not. And this is actually an interesting one. This is really to avoid loss spikes. So for example, if we have a data set, let's say example 1, example 2, and so forth. If we have a data set like that, let me just do it like this. And suppose we have a batch size of 2. What the data loader will do is it will divide the data set into batch sizes of 2. But if the data set size is not divisible by the batch size, you often end up with very small batches at the end, the last batch, because it's the remainder. And this often results in loss spikes, like unstable training. So it's actually a good idea to always remove the last batch. If you do multiple epoch training, you also don't have to worry about missing certain data points by removing them. But also in general, usually data sets are so large that, you know, if you don't use the last batch, doesn't really matter. So it's usually a good idea to have batches of the same size so you don't have these instabilities during training. This is why why I'm recommending dropping the last batch always. And then num workers is for using multiple background processes. I have it here set to 0 because I'm executing this in a notebook. And in some cases, this can be, might not work because notebooks are a bit more restricted than Python scripts in terms of spawning multiple subprocesses. Or if you're using Windows, I think Windows generally has some problems with multiple background processes in Python. So this is just like a safe choice, but yeah, you can try also to set it to a larger number, for example. But yeah, for these purposes in a notebook, this should be fine to set it to 0. And this was very conceptual. A few more things here. We are initializing the tokenizer. This is the tick token tokenizer we talked about earlier. Then we are creating the data set. That is the data set we have up here. And we are creating it with text, and text will be our training data set. And here is where we are creating the data loader using the settings I defined earlier, and we are returning it. So all very, very, I would say conceptual. So let's actually see it in action. And for that, we are going to use the verdict again, which is our short story that we downloaded earlier, the short story by Edith Wharton. Raw text. So this is how it looks like. We have seen it earlier, and now we are going to pass it to our data set and data loader. So let me just, because otherwise it will end up a very long video, let me just copy and paste the code here. We are going to start with a batch size of 1 and a context length of 1 and a stride of 1. And so the batch size is how many samples are in each batch, essentially. The max length is our context length. It's how long the context here is, like the size of the box, how many tokens are in there. And then the stride is by how many places we are moving it. So for simplicity, I will show you stride of 1, and then we will change it. So if this is unclear, wait for a few moments. we will get to it, and whether we shuffle the data or not. And then we are iterating here just for demonstration purposes over the data set manually, and later I will show you a different way to do that. So here we are creating an iteration object, an iter object, and then we are taking the next sample from our data set. So when we are executing this, we can see the next batch here. So this is the first input. It only has a size of 1. And this is then the targets. So you can see the targets are shifted by 1 position. So, and then let's draw another batch. Now what you can see is that the targets here become those inputs. So the first one is always the inputs, the second one is always the targets, because that's how we set up our data set. So the first is the inputs, the second is the targets. Now you can see this is something where it's maybe not ideal, because when we have this input and then the second iteration has this input, there is an overlap. So these tokens are the same. And if you do it like this, the LLM sees certain tokens many, many times, and then it's kind of leading to overfitting. So what's actually better is to increase the stride by 4. So if we do that, you can see each of the tokens are unique. So you can see they are not overlapping anymore. And so what it does is it's moving this box by stride of 4 by 4 positions. So 1, 2, 3, 4, moving it by 4 positions. So we are at the city stood the. And you can see this is what's shown here in the second row. The reason why I showed you just the stride of 1 was so you can see that this actually works and it's not missing any data, because you can see this one picks up right here if we have a stride of 1. I thought this might be more intuitive, but if it is confusing, don't worry about it. Just go to the stride of 4, and then you have exactly what you can see here in the figure. Now, this is for a batch size of 1. When we are training deep neural networks, it's usually efficient to use a larger batch size. So what we can do is we can use a batch size of 8. So I'm just showing you a same thing here. Instead of batch size of 1, I have a batch size of 8, max length of 4, and a stride of 4. And then some labeling so it's a bit more clear. And here you can see now we have the inputs here and the targets. And this is similar to what we are seeing here, where we have multiple rows, where each row is one training example. And so we have a batch size of 1, 2, 3, 4, 5, 6, 7, 8, and then the corresponding targets. Yeah, and this is really how we implement this data loader. And then later we can also iterate over it more efficiently. So this is a topic for later. I just wanted to set up this data loader so that we have one way later on to load the data into the LLM efficiently. We talked a lot about creating token IDs, but now let's take it to the next step and talk about creating token embeddings. So if I go back to an earlier figure from section 2.2, we looked at this figure where I showed you that input text gets converted into tokenized text, and the tokenized text gets converted to token IDs. Now the next step is creating these token embeddings from the token IDs. So essentially taking an ID, an integer value, and converting it to an embedding vector. And so this embedding vector contains real numbers, like floating point numbers, that can then be optimized. So to show you how it works, we are going to use some token IDs as an example, just like as a PyTorch tensor, so that it is a bit more easy to see what's going on. So let's do torch tensor and then insert those. And I should say these are relatively large numbers. So let's actually use some smaller ones so we can have nicer visualization. So these are just like some words or tokens in our input. So we have this input tensor now, and then the next step would be creating a so-called embedding layer. Usually this embedding layer is part of the LLM itself. We will revisit this many times later in this book, but this would be a standalone embedding layer. And there's usually something called the vocabulary size. So this is the size of the tokenizer, the vocabulary tokenizer. And then the output dimension. So this is the vector embedding size. So the vocabulary size is, in our case, for the tick token tokenizer, it's 50,257. Sorry, that is probably not the correct number. Let me double check actually. Tokenizer. One way, if you forget, like me, what the name of the vocabulary is, you can use in Python this dir, and it should actually show you. So vocab. So if I go up here, type vocab, and then we do the length, you can see, oops, it's not a list, it's just an integer. You can see it has 50,257 unique tokens. So this would be one argument for our embedding layer. So it supports all these different tokens. And the other one would be the output dimension. So this would be the desired size for these vectors. We will actually use the original GPT embedding size later on. For simplicity, let's actually use simpler and smaller values, so it's then easier to visualize. So let me use vocab size 6 and output dimension. Let me just copy it. Let's do 3, because 3 is also what we are seeing here, like 3 little boxes per vector. So we have a very small example that is hopefully easy to see. And then one more thing is I'm adding a random seed here. Why am I doing that? It's because this is a neural network layer with random weights. And so the random weights are different each time you instantiate a new layer. And so I just want to make sure you get the same results that I do. So I'm initializing this random seed. And by the way, if random seeds are something you are not familiar with, let me know. I also have a nice video on random seeds I can share with you. But yeah, so this is now this embedding layer. And the embedding layer has a weight matrix. Weight. And so this is something that is later optimized during the neural network training, like the LLM training. And yeah, they are called weight parameters or parameters. And these are things that are going to be adjusted. And by the way, if you are familiar already with linear layers or matrix multiplications and everything, an embedding layer is just an implementation detail to make a certain lookup easier or more efficient. This is more advanced. You don't have to read this if you're not familiar with this, but for those who are curious, I do actually have some bonus material here where it's about understanding the difference between, the difference between embedding layers and linear layers. So if you're curious how this relates to matrix multiplications and linear layers, it's like a short notebook for those who are curious. But if you are not familiar with it, don't worry about it. I will try to explain it in a more, let's say, intuitive sense. So let me show you something. So if I do embedding layer and I call it on, let's say, this input here. Let's just pick one of these numbers, torch tensor. Let's make a smaller tensor and use, let's say, the 3 from here. Let's see what happens. So you can see it's pulling out a vector here. So there's a tensor of 3 different numbers. And if you have a sharp eye, you might notice it's actually this row here from this embedding matrix. So if we are typing 3 here, Python is a 0 indexed. So it's 0, 1, 2, 3. It's giving us this vector from this matrix. And similarly, if I go here and I do, let's use the first one, and I do this one, you can see this one is the first, sorry, not quite, the third row, sorry, 0, 1, 2, because that's the number 2. And this is, yeah, the index 2 corresponding to this row. And similarly, if I now use the whole input IDs, I'm pulling out values from this matrix. So I probably should show them here for reference. So the first one, that's the 2, it corresponds to 0, 1, 2, to this one here. The second one corresponds to this 3, so this would be this row here. The 5, this one, 0, 1, 2, 3, 4, 5, and so forth. So we are essentially, when we are calling this embedding layer on the input IDs, we are pulling out vectors from this matrix. And this matrix technically has the size of our tokenizer. So I can just show you this example, tokenizer.n vocab, right? So in this case, this might be a very large one. Should I print it? Maybe let's try and see what happens. It's actually dotting it out. But yeah, this would be then 50,257 rows essentially. And yeah, this is essentially the embedding layer that is used to convert the token IDs here into these vectors. And this is usually part of the LLM. And yeah, these numbers I mentioned before, they are random. So if I actually comment this out, you might see these numbers change because the weight matrix, the weight matrix changes. And so usually what we want to do is we want to start with small random numbers. It doesn't really matter what these numbers are, but later on during the training, these numbers get optimized in a sense that the LLM is optimized end to end to produce the desired text, the next word in the training text. And so don't worry about why these numbers are random yet, because they're not trained yet. They're just starting values. We're going to train them later in chapter 5. But now, yeah, you have a hopefully good understanding what an embedding is. So an embedding is a vector from this embedding matrix that gets later trained. So now that we understand word embeddings, let's take it a step further and add positional information. I will tell you in a few moments what the positional information means, but yeah, just to recap, we had input text, we tokenized the input text, created token IDs, and then the previous section was focused on creating these so-called token embeddings. And we only had a very small toy example. And then just to use the actual sizes for our tokenizer, we mentioned our tokenizer has 50,257 words. And so we pass this vocab size to our embedding layer to create it in this size. And now we also scale this a little bit up, because before, we had like an output dimension of 1, 2, 3 tokens, which is just for a toy example. Now we are increasing it to 256, which is what we are going to use to train the LLM later. It's a more realistic size. GPT-2 was originally trained with output dimension of, I think, 1024. I'm not quite sure. I would have to double check. But yeah, this would be something that works also well on a small computer, like a laptop, for example. You can always, try larger values if your computer supports it, but I think this should be supported on most hardware for demonstration purposes, but also to make it a bit more realistic than having an embedding size of just 3 dimensions. So we have now 256 dimensions. So if we do that, so we have our embedding matrix that has 50,000 rows and about 200 columns. So that's our weight matrix, similar to what we did before. Now, taking it a step further, we had also the data loader. How does it now come together with these embeddings? Previously, we created these token IDs. So if I just show you this, it's the same that we've covered earlier. So we have a data loader that creates batches of size 8 with a max length of 4. So 4 token IDs per training example. And then we have 8 examples. And so now, how does it actually relate to the token embedding that we have seen in the previous section? So what we do now is we actually convert these token IDs into these embedding vectors. So if I do that, what I showed you earlier is if I take this and I type input IDs, it would create the sample vectors for the simple input IDs that we talked about earlier. But now we are going to use actually the data batch here. So this would be the data batch that we convert, and let's maybe call this token embeddings, and let's just see what happens. And let's actually look at the size of the output here. So you can see now we have still the batch size of 8. So it's now a three-dimensional tensor, and the numbers correspond to the batch size. So we have 1, 2, 3, 4, 5, 6, 7, 8 rows, 8 examples. Each example has 4 tokens, like 1, 2, whoops, 1, 2, 3, 4. But now it's not just the token ID. Each one of those is actually a 256 dimensional vector. So here, each token ID gets converted to a three-dimensional vector. Now it's a 256 dimensional vector. It's hard to visualize vectors in 256 dimensions, but we can actually maybe print one of those out. So if we take a look at the first one, first batch, the first token, this should give us yeah, the vector, the 256 dimensional vector corresponding to the first token in the first batch, basically this one. Okay, so now we converted token IDs into token embeddings. The next step is adding positional information. So let me see if I have a nice figure for this. So previously what we've done is we pulled out these embedding vectors from the weight matrix for each input example. And so I previously chose an input that was, yeah, I would say relatively nice for explanation purposes, where each output row looked different. So we had fox jumps over dog. These are token IDs corresponding to an example input like this. And then we pulled out these embedding vectors corresponding to the token IDs from this weight matrix. Now, what happens if we have the same token ID? For example, fox jumps over fox. So here, this token index 2 is the third row in the weight matrix. And so we get, as the result, this row here. But since in the last token ID, we have the same word, the same token ID, it has the same vector. I mean, it makes sense, right? We are looking up the position here. We are pulling out the vector and create the output like that. Now, this is fine. It would work, but we could actually add some more information to it. So to provide more information to the LLM, depending on where this word is located in the input, we can create so-called positional embedding information. There are different ways you can do that. So GPT-2 used a very simple way. It used a second embedding layer. There are nowadays other ways, for example, using rotational positional embeddings. If you're curious about those, in the bonus material on my GitHub repository, I implemented also Llama 3.2 from scratch. It's more advanced and more complicated, and it's not as nicely described as in the book, but they use something called rope embeddings that I also implemented here. But GPT is, yeah, fortunately much simpler in this case with the embeddings. It's using simply a second embedding layer. So let me actually show you how that would work. So we are using the same embedding class we used before, but now we have a token embedding layer. In addition, we have now a position embedding layer where we add positional information. So the goal will be, maybe I have a figure. Yeah, I do have a figure on that. If we have input embeddings like this, the goal is to have a second set of values that we add here. So positional embeddings that we add. So we have, token embeddings. So to step through this figure more slowly, I chose the same token embeddings for each example here, just to keep things simple. So if we have just input that consists of the same word, like fox, 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 for example, the token embeddings would be the same in all the cases, but then we add positional information on top of that so that the actual input embeddings look different depending on where it's located. Now I'm using these very nice numbers where it's easy to read those numbers. In reality, these are all starting with random numbers, so it doesn't look quite as nice. But these numbers, the positional embedding numbers, they also get optimized automatically later during the LLM training. So they are random numbers to start with, and later they will get optimized similar to the token embeddings. So here, yeah, I'm creating a second position embedding layer essentially. And then what I'm doing, so here is the max length. So the max length is, yeah, how many inputs are supported. In this case, we only have 4, right? So we had a max length of 4. 1, 2, 3, 4, it can only support 4 input tokens. In practice, this is a much bigger layer. So for simplicity, we just keep it small for visualization purposes and just simplicity. Later, when we train the LLM, we will actually use much larger values. And then what we can do is we can use torch A range. So A range is creating in sequential order values here, 0, 1, 2, and 3. So 0, 1, 2, 3 is just a tensor, it's a placeholder tensor for the positions, position 0, position 1, 2, and 3. And we have this position embedding matrix, and it's a similar matrix to what we had before. Oops. And then when we are calling this with our A range, what it will do, it will just pull out the values like in sequential order here. So you can see it here. So it's just getting me the values here. And that is all that is really happening in this positional embedding layer. And then what we do is we add them on top of each other. So maybe to go before I execute this, this one has shape 8, 4, 256. And this one should have the same shape. So we can then add them to each other. I have not executed this right here. So I'm sorry. This is actually only for 256 because how PyTorch works, I mean, for efficiency, we don't need to duplicate this over the batch dimension because this one will be added to each batch separately. So what happens is essentially that when we have something like this, the input embedding has the same size as the token embedding has the same dimension as the position embeddings, and then the input embedding will also have the same dimension. So here, the concept is called broadcasting in PyTorch. So let me maybe show it to you like this. So when we do this, we can add these values together. So this is the first example in the training set, and then our position embedding vector. And this would be essentially similar to doing this, except now we are doing it for all the examples in the batch. But the first example, maybe you can see it here, should be similar. So you can see this one is similar to this one. I mean, this is like a rounding thing, not a rounding thing, a different print representation, but this row is the same as this row essentially, and so forth. So this is just generalizing it over the whole batch dimension. Oops, let me just clean this up a bit. And then when I add them together like before, the shape should be the same as before. So we are just adding this additional position information to it. And so with that, we now have covered the whole input pipeline. So we have input text that we break down into tokenized text. Then we convert it into token IDs. Then we create these token embeddings with our token embedding layer. We create the position embeddings, add them together to get the input embeddings. And so this is all we need to know for now for the data preparation step. Next, let's actually tackle the inside of the GPT-like decoder only transformer. So what is actually inside the model? One more thing I should say, the embedding layers are technically part of the GPT model, as we will see later. I just draw them outside here because it's a bit easier to talk about it since we already talked about the data loader. But yeah, in the next chapter, we will talk more about the attention mechanism that is inside of a GPT model. So I hope this was useful, and I hope I will see you in the next video.